Imagine a shape with an infinitely long boundary that still fits inside a finite area. It sounds impossible, but over 100 years ago, a mathematician discovered this exact shape. In this video, we're going to build the shape step by step and discover why something impossible is actually true. It all begins with an equilateral triangle, a triangle whose sides are the same length. Let's take a side and divide it into thirds. Now, taking the middle third, let's use this to make a miniature equilateral triangle. So we get this little spike. And now let's do the same for each side. Our new shape now has 12 sides. And let's repeat the process again. We take a side, split it into thirds, replace the middle third with a triangle, and put it back. And let's do this for the other 11 sides as well. But why stop here? Let's do it again. What happens if we never stop and keep replacing the middle segments with little equilateral triangles? First, let's observe what happens to the perimeter. We'll begin with our original equilateral triangle. All the sides are the same length. So if we set the length to 1, then we know the perimeter of the triangle is 3. When we take a side, split it into thirds, and make a triangle, what happens to the length of the side? Well, the side is now comprised of 4 segments. Each segment is 1/3 of the original length. This means that the new side has a length of 4/3. Repeating the process for the remaining sides of the triangle, we find that there are 3 sides that are 4/3 long. From this, we can calculate the perimeter of our new shape. That's 4 units long. Now, each side in this 12-sided polygon is 1/3 of the original length, meaning when we repeat the process and split one of these sides into thirds, each new segment will have a length of 1/9. Setting up the triangle in the middle will again produce 4 segments. Thus, each new side will have a length of 4/9. And repeating this process for each side, we can calculate the perimeter, and we are left with 16/3. That's the perimeter of this this 48-sided polygon. Now we have successfully completed the first few iterations of our snowflake shape. Can you spot the pattern of the snowflake's perimeter? The first shape had a perimeter of 3, the second a perimeter of 4, and the third a perimeter of 16/3. Notice that to find the next perimeter, we are just multiplying the previous one by 4/3. Using this knowledge, we know that the perimeter of the following 192 gon must be 64/9. Patterns demand a general formula. The perimeter after the nth iteration is just the first perimeter times 4/3 n times. So the perimeter of the next 768 gon is 3 times 4/3 to the power of 4. That's a perimeter of 256/27. Our finished snowflake is the result of infinitely many iterations, each adding tinier and tinier triangles. So to find the perimeter, we can observe what happens to the formula as the number of iterations approaches infinity. Since 4/3 is greater than 1, we find that the perimeter is infinite. Now, pause. You may be thinking, duh, obviously the perimeter is infinite because we are adding infinitely many triangles to each side. But that's what makes this next part so bizarre. The area is finite. Once again, let's trace our roots back to our triangular origin. And let's say the area of this triangle is A0. Well, then if we take a side, split it into thirds, and add a triangle, how much area are we adding? We know the sides of the new triangle are 1/3 of the original length. Area scales with the square of the side length. So the area of this triangle is 1/9 of the original area. For ease of mind, here's 9 of those triangles in the original triangle. There are 3 sides in total, so we add 3 triangles. This means that altogether, these little triangles added 3/9, or 1/3 of the original area to the shape. Now, when we repeat, each side is 1/3 in length. So when we split this side into thirds, the new triangles will be 1/9 the original length. To find the area of the new triangle, we square the length, yielding 1/81. When we do this to all 12 sides, we have 12 triangles, each with an 81th of the original area, meaning this iteration just added another 4/27ths of the original area. This process continues forever, so like before, let's see if we can spot a pattern. We care about the added areas. From the dodecagon to the 48gon, we see that the added area is 4/9 times the previous area. This makes sense, because each time we add a triangle to the side, we get 4 new sides that weren't there previously. 4 sides means 4 more future triangles. Each of these triangles will only have 1/9 of the previous area, since each side is 1/3 of the previous segment. So 4/9 is our common ratio. To find the next area, we just multiply the previous area by this ratio. 16/243. Can you construct the general formula? We start with the initial area, A0, and add 1/3 of the initial area. Following that, each time we iterate, we add 4/9 of the previous area. This is a lot of notation, so let's condense it. We notice that we are just multiplying by powers of 4/9. To make this more evident, we can add 4/9 to the power of 0 to the second term. Also, notice that from the second term onward, each term is multiplied by 1/3 A0. All of this is being added together, so we can use summation notation. This is just the initial area plus the sum of all the powers from 4/9 from 0 to n times 1/3 of the initial area. So this notation here symbolizes the area of the nth iteration. Remember, our snowflake adds little triangles forever, so the total area will demand an infinite sum. In our summation, we can factor out the 1/3 times A0 since this is a constant. And now we are dealing with a geometric series since we are just multiplying 4/9, our ratio, repeatedly. Notice that our ratio is less than 1. This means that our series will converge. Our final sum will approach some finite value and will not go to infinity. For converging geometric series, we have a formula that we can use to find the final sum. We just need to put in our ratio, 4/9, and let the math do its work. This infinite sum equals 9/5. After simplifying the second term with some multiplication and combining like terms, we find that the area of the final snowflake is 8/5 of the area of our humble triangle. Even though we are adding infinitely more triangles, their areas shrink fast enough to give us a finite amount. This is where our snowflake reveals something truly remarkable. We started with nothing more than an ordinary triangle. After adding triangle after triangle to the sides, something extraordinary happened. Its perimeter continued growing infinitely, yet its area settled to a perfectly finite number. The same shape is both infinitely long and finitely large. We call this shape the Koch Snowflake.